Part 3 of Unit 11 is about manipulating the equilibrium constant. There's a special relationship between Kc, equilibrium constant for concentrations, molarity, and Kp, equilibrium constant when pressures are used. This equation is on the green sheet, but we'll go ahead and go over it here. That relationship is that Kp is equal to Kc when that's multiplied by RT to the delta N power. Now, these are the two equilibrium constants. Sometimes you'll be given Kc and have to convert it to Kp. Other times you're given Kp and have to solve for Kc, but that's pretty easy. R is our gas constant, 0.0821, because we're usually going to be using atmospheres. T is your temperature in Kelvin. And delta N is equal to the change in number of moles of gas. And how that works is you subtract the moles of the gas reactants from the moles of the gas products. So you add up the coefficients of all the gases in an equation, the reactants and the product side, and then you subtract the reactants from the products minus the reactants, and that'll tell you what delta N is. So for this equation of 2H2O2 decomposing to H2O and O2, let's pretend that these are all gases. Delta N for this would be 2 plus 1 is 3 minus the 2 over here, so delta N would be 1. It's the sum of the moles of the gas products minus the sum of the moles of the gas reactants. The equilibrium constant of a reaction in the reverse direction is the reciprocal of the equilibrium constant in the forward direction. We went over the equilibrium expressions for these two in an earlier video, but if we just called this equilibrium constant K, when we flip this equation and put it in the reverse direction, the equilibrium constant becomes the reciprocal of that, or 1 over K, because you flip where the products and reactants are in your equilibrium expression. The equilibrium constant of a reaction that has been multiplied by a number is the equilibrium constant raised to a power that is equal to that number. So in this example, we've got our N2O4 reaction, and it's multiplied by a coefficient of 2. N2O4 gets a 2, this 2 becomes a 4. We don't multiply the equilibrium constant by 2, we raise it to the second power. So K here is K squared from earlier. If it was multiplied by a 3, if we had a 3 here and a 6 here, we wouldn't multiply K by 3, we would raise it to the third power. So you just have to remember it's an exponent, not a coefficient that you multiply the equilibrium constant by. The equilibrium constant for a net reaction made up of 2 or more steps is the product of the equilibrium constants for the individual steps. So we've seen in Hess's law problems and kinetics mechanisms adding steps together. We don't add the equilibrium constants even though we're adding the reactions. We multiply the equilibrium constants together. So let's look at an example. We've got 2NO2 yields NO3 plus NO. And our other reaction, we'll call it NO3 plus CO yields NO2 plus CO2. We'll call this K1 and this K2. First, we're going to determine the overall reaction. Got to cancel out any intermediates like NO3. And we actually can cancel out one of the NO2s as well. Now we're going to add everything else together, so NO2 plus CO yields NO plus CO2. That's our overall reaction. We added the steps together. You'll have an equilibrium constant value for each reaction. You don't add those together, you multiply them. So our equilibrium constant for this overall reaction is K1 times K2. Your question for this section: using the information above, calculate the value of K for the following reaction. 2NO plus Br2 yields 2NOBr.